So hello everyone, I am Babu Subash Chandar from Cyberlogic Systems. So my talk is about. So we have discussed a very extensive topic on AI and other high-level stuff there. My topic is like going under the hood, what is happening under the hood in the Linux wireless stack. So this is kind of a curiosity-driven experiment that I had in my team and to identify what actually happens and who actually creates the frames in the wireless stack. So, so we'll talk about the perspective that we are going to build and the real frames, 8 not 11 frames in the wireless stack. What is actually inside the wireless stack, and we are trying to map the wireless stack with the 8 not 11 model, and on top of that mapping, we'll try to pin this frame onto a particular component in the wireless stack. And at the end, we'll have a takeaways of what this experiment has given to us. So firstly, we'll provide a different perspective on the 8 not 11 frames. So we have different types of frames available out there. We'll try to build a categorization, not as what the standard says. We'll try to introduce the wireless stack on the Linux soft Mac devices, and we'll try to map the wireless stack with the 8 not 11 management model, and we'll try to pin those frames on top of it. So this perspective is not an absolute model that we can pin a particular frame on a particular component. It is kind of a compass of direction that gives you to close in on a particular frame in the component rather than a GPS coordinate of a particular frame. So a typical classification of 8 not 11 frames are like management, control, and data frames. So your management plays the policy brain, and the control frames are the traffic signals, and the data frames are the real payload that we want to transfer between to the stations. So instead of this type of classification, we'll try to form a different uh, model of classification or categorization in per se. So those are the four lenses we have. One is a sequential. The sequential is when the standard says after this frame, the next frame will go. That kind of a sequential will give you a different perspective of what goes next and what initiates the next frame. The next thing is on the role. We have AP star and multiple roles in the Wi-Fi. So a role actually plays a different perspective of what actually generates a frame in the wireless medium. So whether a AP initiates a particular frame or a star initiates a particular frame. And we have timing requirements that are very crucial in certain frames that are very strict, stringent timing requirements. And we are going to talk about the trigger, who pulls the trigger when a frame is initiated and it's on the medium. So on the sequential and role based perspective, we have this infamous phases of association. AP star communicates with each other in these sequential fashion. We have probe request and all this list of frames. So this model is non-negotiable. We have to go through this sequence. We have to go through these phases, and that too on these roles will play those frames, and other role will send only those frames. This is a different categorization that we have. And on the timing requirements, so for on a non-RTS CTS based data exchange, we have a data sent by a transmitter to a receiver, and on the requirement timing requirement perspective, we have the CIFS requirement that is 10 microseconds for legacy based devices and 16 microseconds for uh, the contemporary systems. So the ACK has to go to the transmitter when the data is received within that time stringent uh, period. So when it is a RTA CTS based exchange, the RTS and CTS should go in hand with that time stringent requirement. And on the right side, we have the block accession. When you have the aggregated MPDU, at the reception of the last MPDU, there is a timing requirement that you have to send the ACK within the 16 microseconds or 10 microseconds. So this is the a different categorization that I want to project here. Uh, any frame that is initiating from the station can have these categorizations. Like it can be initiated by an user event. For example, a star is trying to scan. It sends the probe request. It is initiated by the user. If it's an event, like for example, if it is a AP sends a association response. So it is based on an event that is got by the station that it is trying to associate with it. So there is also timer based triggers, which is a typical beacon frame, which is always fires at 100 milliseconds, right? That is on the timer trigger. There are something on the scheduled category. There is something on the nearby impact. The nearby impact, I mean the environmental factors. For example, if it is a DFS trigger, we'll send a CSA and then we switch to a channel. So the quality of experience is based on the mesh networks where we have BTM, RRM, and uh, other activities on top of it. So these are the frames that I wanted to categorize on these initiation-based model. On the user's event triggered, we have probe request, deauthentication, dissociation. All of them are user driven. So for example, if a data is sent across the wireless medium, the data will be sent on the by the network stack based on a user trigger. When I wanted to share a movie with my peer, I will send through Wi-Fi and it is initiated by the user. The event trigger is when it is based on a probe response is received only when a probe request is achieved. That is because of the previous frame that is received. So when there is a timer or event triggered, we have when it is, for example, a beacon is there, it is always scheduled on a particular timing. It is a state transition based frames or authentication, association request, re-association request, and the null data here is a power management based frame, but it is also a state transition that we can count on. On the scheduled categorization, we have trigger frames, beamforming report frames, where OFDMA based systems will have trigger frames to schedule the stations on to access the medium. So on the nearby impact, environmental factors like DFS or the interferences, non-Wi-Fi interferences also impact the Wi-Fi to take some decisions, and some frames will initiate based on that as well. On the quality of experience, we have when the AP is loaded, for example, if it is 2.4G is loaded more, it uses a BTM request and it set a client to nearby its own band of 5G, or it can also give a neighbor request to move the station to nearby good AP. The EAPOL four-way handshake that I mentioned here in the quality of experience is because it gives the network access. The EAPOL four-way handshake is a data frame uh, which is only appearing in the air to allow the access to a station on the medium. So let's move on to the Linux wireless stack. This is a typical Linux wireless stack of softmac based devices. So here on the left side, we have the Ethernet driver with the network stack on top of it. Till that point where you have the protocol agnostics and the network protocols, we have the network stack. And below that is an Ethernet driver and the Ethernet device. On the right side, we have all the components of the wireless stack. The management interface, which is host APD, IW, and WPA supplicant, that talks to the kernel drivers through NL 8011, CFG 8011. These are the glue logic that is trying to access the kernel sources. So Mac 801 is the heart of this wireless stack, where you have the soft Mac driver is available. The Wi-Fi driver is the device driver that handles the radio interactions on the Wi-Fi device. So in that note, we have a timing possibility on each of these component in the wireless stack based on various measurements by the internet. And the user space threshold of activities that is done in the post APD, IW, and WPA supplicant will run around like 10 milliseconds to few hundred milliseconds. The Mac 801 soft Mac driver, the threshold is around based on the soft IRQ and the interrupt latency and all that counts to 1 millisecond to few milliseconds. On the Linux virus driver, we can achieve around 100 microseconds to 1 millisecond. And the most heavyweighting timing requirement, stringent requirement can be done by the firmware. So this is the management model 8.11 standards usually have at the very first few chapters of the standards. You have the MLME, PLME, SME, HLE, and on the left side we have what is inside the MAC and PHY of the wireless devices. So we wanted to map this management model on top of the Linux wireless stack. So to understand or to map the frames that we categorized earlier on top of this model, which is mapping on the Linux wireless stack. So this is a fair amount of grouping happening on top of Linux wireless stack using the management model. So you have SME on top of the stack, that is host APD and WP supplicant. The SME, MLME SAP and SME PLME SAP. Thanks. So SME, PLME SAP will be clubbed together in the NL 8.11 and CFG 8.11. The soft Mac, Mac 8.11 will act as a MLME here. It will do the state transitions. The policy will be driven by the SME. All the policies will be taken care by the SME, and the framings will be done by the MLME. It will be transferred to the PHY through the wireless driver. On the left side, we have the network stack. The network stack is the responsibility of the network stack is to transfer all the data from the user to the Mac 8.11 soft Mac devices. So we have mapped wireless stack on top of the 8.11 management model. We are now trying to pinpoint the categories that we have discussed on top of this management model mapped on top of the wireless stack. So first we need to understand as the Wi-Fi standards are evolving and as the Linux wireless stack is being evolved for multiple standards. So pinpointing a particular frame on a particular component is not very accurate. We can say at one point of time, one point of version, we can say this is a approximate idea of where the frame will be sitting. So there are multiple factors that would affect this model, that are the design decision that is taken at the wireless drivers or the soft Mac drivers, the vendor lock-ins that happens, and very predominantly that one discussed earlier, right? The timing requirement, the stringent timing requirement is playing a key role here in understanding where the stack is crafting the frame. So in the open source, Linux wireless stack actually provides us the flexibility to enhance and extend the functionalities of the SME or the MLME slightly above the stack to the user space. So that is where your RRM and other AI algorithms that runs to craft the frames, not within the stack, even above the stack as well. So the stack component involved for the state transition based management frame initiation is on the SME, because that SME is the policy brain of the whole stack. All the management frames will be crafted, and some of the time relaxed control frames will also be crafted by the MLME component, so which is the MAC 8.11. As we already discussed, the time stringent requirement of certain frames, which is the SIFs, right, SIFs. Those time critical frames will be generated or crafted at the firmware without the knowledge of the kernel or above stacks that is above it. So all our data frames are user driven, and those are generated by the network stack. The network stack will deliver those data frames to the MAC 8.11. So with that note, we can have key takeaways like different perspectives of the frames give us a close-in of a particular frame on a Linux wireless stack. The vocabulary of 8.11 management model will allow us to close in on the frame on a particular component in the wireless stack. So it also there is also a time requirement that says where exactly the frame is crafted in the stack. So it is only give you an approximation of where in which component in the stack a frame can be crafted. So with this information, I think we can have a fair idea of approximately closing on a frame in the stack. Most of the policies will be driven by the SME. Crafting will be happening in the MLME, and actual sending will be done by the firmware. So thank you. That is.
Thanks. Thanks for finishing on time. Just before the tea break, any questions you have? Vardhan mentioned the key people Chennai had. So Sendil, maybe I request you to get up one of the key open source people in Wi-Fi across the globe. We should honor. So since we had an open source stack, Sendil has been one of the key people. So people might not know, but Sendil has had very unique contribution. So quick 1 or 2 questions before Vardhan takes over. Anybody for Babu? Everybody seems to be looking forward to the tea break. So Sendil has a question. So expect some difficult question. Yeah.
I think it's an excellent presentation. Not a question, but I think the evolution of open source, right? The post-APD, when we brought host APD initial days way back in 1998, right? The idea is to, help the key exchanges, right? The key negotiations. That's the primary motive. Part of the .11x, .1x, that is how it was evolved, right? And that is how it started. Then later on, the user space MLME concept have, taken place in the Linux kernel upstream. So a lot of, if you look at the Wi-Fi station SME, for example, that still happens within the Linux kernel. In fact, there are concepts in WPS applicant where we leverage that, but SME is still in Linux kernel for the station mode, whereas for the AP mode, option of SME moved to the host APD, because the Linux kernel update is going to be very difficult, especially after it is launched. Whereas for an application-based upgrades is much easier than Linux kernel upgrade.
Exactly.
That's one of the reasons the kernel community has come up with this user space MLME for OSAPD. So that's one of the data point that I just wanted to add. Otherwise, it's an excellent presentation. Thank you.
Thank you.